We are talking about subgroups. So if G is a group, a subset H of G is called a subgroup of G. If H itself becomes a group with the group law and the identity element taken from the group G. So it's like is G, H is a subset which becomes a group itself when you take the operations from G and the identity element. And we use this notation H less than or equal to G to mean H is a subgroup of G. We gave a couple of examples and I want to give more examples, but before that we need this lemma which helps us recognize a subgroup when you see one. So here's what it says. Let G be a group and H be a subset of G. Then H is a subgroup of G if and only if the identity is in H, and whenever two elements are in H, then their product is in H and the inverses are in H. And then there's a third statement which is also equivalent. This is same as saying that H is non-empty, and whenever two things are in H, the inverse of the first one times the second one is also in H. 2 and 3 we'll see are very closely related. I mean 3 is just a little more convenient sometimes. So let's prove this thing. 1 implies 2, I'll leave as an exercise. I mean, if it's a subgroup, then it has, if it's a subgroup with the operation and identity borrowed from G, then of course it has the identity of G. That's clear. And if it's a subgroup, then product of two elements are there, and the inverse, every element has an inverse. So 1 implies 2 is very clear. I mean, 2 implies 1 is almost equally clear, but I want to write out something. So let's write down something. So assume 2. The main point is that if you have this condition, by the way, when you have this condition, we say that H is closed under multiplication. That whenever two elements are in H, then their product is in H. And if you have this condition that if A is in H, then A inverse is in H, that is called closure under inverse. So 2 is saying, really, this condition 2 here is saying that H contains identity and H is closed under multiplication and taking inverse. Okay. So let's assume 2 and see why H has to be a subgroup. The point is that if H is closed under multiplication, that tells you that this multiplication map is really a map from H cross H to H. Let me write that down. Since A comma B in H implies A times B is in H, we see that the multiplication is a binary operation on H. And by this dot, I mean the multiplication law of G. So this is the group law of G. If you give me two things in H, then the product better be in H, if H has to be a subgroup. Because H has to be a group in its own right. So that's what this closure under multiplication ensures. And once you have that, you know that G already satisfies the group axiom. Now we need to verify. So on, for example, A times B times C is A times B times C for all A, B, C in G. So of course A times B times C is A times B times C for all A, B, C in H. Maybe I should say, since A is a subset of G. Since H is a subset of G, we have this. Because if this formula holds for all things in this bigger set, then this formula also holds for all elements in the smaller set. So that's the associativity axiom. Similarly, you check the identity axiom because you have the identity in H. In H, we similarly verify identity axiom. And then finally, since A in H implies A inverse in H, the subset H satisfies the inverse axiom. That says that given any element in the set, there has to be another element such that when you multiply them together in either order, you get the identity. We know that there is such an element in G, and this condition here tells you that that element actually lies in your smaller subset H. Okay, so H is a group in its own right. And that's basically the essence of the argument. And that's how this lemma is often used. You want to check that something is a subgroup, you check these conditions. Okay. And then maybe I'll also point out how you go from 3 to 2. Because that's sometimes convenient. So if H is, and this is not much, this is just a little fiddling around. H is non-empty, we can choose some element there. Now, I have to show that the identity is there. Well, the identity is A inverse times A. Now A is in H, A is in H, so A inverse A is in H. That's this condition. Whenever A and B is in H, the inverse of A times B is in H. I'm taking A and B to be both A. That's true. So the identity is in H. I get that. Now, since A is in H and E is in H, by E I mean this E, I get that A inverse times E is in H. But A inverse times E is just A inverse. So, what did I see? If A is in H, then A inverse is in H. Maybe I shouldn't use the same A. So let's choose some B. So what we have argued is if B is in H, then B inverse is in H. So the subset H is closed under inverse. And now for multiplication, choose A comma B is in H. Then by this step, I know that A inverse is in H because we just showed that H is closed under inverse. And now A inverse is in H and B is in H. So A inverse times B is in H. But that's AB. Okay. So this is nothing serious, just tricking with symbols. But that would be sometimes convenient to check. Okay. Now maybe I'll give a couple more examples. We saw some examples here. So maybe let's look at this group that we studied in the beginning, symmetries of the square. So really meant reflection and rotational symmetries of the square, right? So this had 8 elements, if you remember. The identity rotation by 90 degree, rotation by 180 degree, rotation by 270 degree, and then 4 reflections. I call them flip 1, flip 2, flip 3, flip 4. I claim that if you just take the rotations, this is a subgroup. Because if you take one rotation and compose it with another rotation, you again get a rotation. You never get a reflection. And the inverse of a rotation is again a rotation. So the inverse of R1 is R3, and the inverse of R2 is R2. And of course the inverse of identity is just identity. So this subset is closed under multiplication and inverse, and it also contains the identity. So it forms a smaller group in its own right. You can call this group the group of rotational symmetries. So this is just the rotational symmetries of the square. But if you just take the identity and the flips, then this is not a subgroup. Because we checked, and this one does contain identity still, and this is also actually closed under inverse, because each flip is its own inverse. Doing a reflection twice just gives you identity, but this is not closed under multiplication. For example, we checked that if you take this horizontal reflection and then take a reflection around this line, first do this reflection, then do that reflection. The net effect of that is a rotation. So reflection composed with another reflection is sometimes a rotation. But the rotations are not in this subset. So this is not closed under multiplication, so it's not a subgroup. Maybe I can sneak in a couple more interesting ones. And then we'll continue with this list next time. So let's look at C star. This is non-zero complex numbers, and the group operation is multiplication, and the identity is 1. In this you have this rather interesting subgroup called, I'll call it S1 for the circle. These are all complex numbers that have absolute value 1. I call it the circle because the absolute value 1 complex numbers, if you picture the complex numbers by points in the plane, then the absolute value 1 complex numbers are exactly the points on the unit circle. And if you know how multiplication of complex numbers work, if you take a point on this unit circle, that's a point of absolute value 1, and it looks like this, e to the I theta. If this angle is theta, this is cosine theta plus I sine theta. And if you take 2 of these, then their product is again on that circle. It's just angle just adds up, and the inverse is again in that circle. You just go the other way. The inverse of this point is that point. Here is one final example. We had this group, rather very important group, n by n invertible matrices. In there, consider all matrices of determinant 1. So this is all n by n real matrices that have determinant 1. You can check that product of two things of determinant 1 is again determinant 1 because the determinant is multiplicative. An inverse of determinant 1 matrix is again determinant 1, and the identity has determinant 1. So this is a subgroup. We'll give more